Your lecturers are Professor Shana Kelly and Professor Ted Sargent. Dr. Kelly is a professor and former director of the Division of Biomolecular Sciences at the Leslie Dan Faculty of Pharmacy at the University of Toronto. She received her PhD in chemistry from the California Institute of Technology. Professor Kelly's research has been featured in Scientific American and Nature Medicine, among other publications. She currently serves as Chief Technology Officer for a firm she co-founded based on her work in biomolecular sensing. Dr. Sargent holds the Canada Research Chair in Nanotechnology in the Edward S. Rogers Senior Department of Electrical and Computer Engineering at the University of Toronto, where he has also received his PhD. His research has been disseminated in leading scientific journals, and he is the author of The Dance of Molecules: How Nanotechnology is Changing Our Lives. Professor Sargent serves as Chief Technology Officer and Director of Envisage Technologies, a firm he founded.
Hello, welcome to nanoscience and the applications of nanoscience that we call nanotechnology. My name is Ted Sargent. I'm a professor of electrical and computer engineering at the University of Toronto. And with my colleague, Professor Shana Kelly, also from U of T, we will explore together the world of nanoscience and its applications. What does nano mean? Nano is referring to the nanometer. So it's a unit of measure, and it's incredibly small. How small is it? Well, let's start with something that we can picture, something we can visualize. A grain of sand is about a millimeter. It's about 1,000th of a meter. What about things that are much smaller than that? Things that we may not be able to see unaided, something we'd need a microscope for. Well, the particles that constitute clay are about 1,000 times smaller than the familiar grain of sand. Very hard to see these as particles on our own. Typically would need an optical microscope. The same thing with the cells that are in our body or with bacteria. They're also about 1,000,000th of a meter, a micrometer. The nanometer is 1,000 times smaller than that. In fact, optical microscopes don't allow us to visualize nanoparticles. We're limited in our ability to resolve images by the wavelength of the light or other particle that we're using to look at something, to image something. And so with an optical microscope, we're limited to the wavelength of the light that we use. Well, that too has a measure of length, that wavelength. It's a bit smaller than a micrometer. Light's actually measured in the 500 nanometer kind of length scale. As a result, we can't typically resolve things that are smaller than that. So we need to turn to other methods to be able to visualize the world on the scale of the nanometer. Take a look at these images, which actually show individually resolved atoms. This is a cross-section of a semiconductor device used in one of the integrated circuits that's inside your computer or that's inside your cell phone. And it's showing that we're able to use what's called transmission electron microscopy, TEM, to see a slice of material and to visualize its individual atoms. Some of the layers that we're looking at here are just a few nanometers thick. The number of atoms that constitutes their thickness in the vertical direction is countable. It can be 5 or 10. Atoms tend to be spaced out in solid matter on the scale of maybe half a nanometer. So by venturing into the world of nanoscience, we're venturing down to the length scale of atoms and also of molecules. And what's so remarkable, I think you wouldn't necessarily expect this, but what's so remarkable is that it is an incredibly visual world. It's something we can't visualize with our own eyes. It's something we can't visualize with a microscope, but it's something that we can visualize with the aid of very special microscopes whose designer purpose is to allow us to see at this length scale. In fact, there's other tools that we have at our disposal as well. The scanning tunneling microscope, such as the one that took this image, allows even finer resolution. We can skate across a surface. We can see individual bumps. We can feel the bumps with the tip of a microscope that traces across the surface. And we can see the egg carton-like shapes that atoms packed into a perfectly ordered array make up. In fact, we can even see, we can even feel the way in which their electrons' waves are shaped. And so our ability to see, using what we now call nanoscience, the field in which we seek to understand at a deep level the constituents of matter on the atomic, on the nanometer length scale, we can visualize matter at this scale today. In fact, when you think of the scanning tunneling microscope and the transmission electron microscope, it's an interesting convergence. These two inventions are very far apart in time. The transmission electron microscope was invented around 1937, and the scanning tunneling microscope around 1980. And yet the inventors of these very different types of imaging shared the 1986 Nobel Prize in Physics together. This must be one of the Nobel Prizes in Physics shared by people separated most in time in the periods of their inventions. It was Ernst Röske who won the prize for the TEM. And it also illustrates another interesting point about nanoscience, which is, we think of it as kind of a revolution that's unfolding today, something new. And it is a very lively field. Huge numbers of scientists and engineers are passionate about it and are engaged in it. But the foundations, our ability to visualize matter at the nanometer length scale, the foundations necessarily go back many, many decades. It's the scientific discoveries that were made before we started using terms like nanotechnology. In fact, even the first initial use of the word nanometer was around 1960. Well, it was well before that, before we were speaking in nanometers, that we were doing the foundational basic science that enabled us to visualize and to have dexterity at the nanometer length scale. In fact, another example of some early important work in nanotechnology before the word was even utilized popularly was Richard Feynman. Richard Feynman, a very distinguished professor at Caltech, also a Nobel Prize winner in physics, who in 1959 proclaimed there's plenty of room at the bottom. There's plenty of capability for us to increase our dexterity in manipulating matter on smaller and smaller length scales. He thought of miniaturization. He thought of packing more and more information. He talked about writing the entire contents of the Encyclopedia Britannica on the head of a pin. And his ability to visualize how much we could do if we could become dexterous on this new length scale was remarkable. And it foresees a lot of what's important about nanotechnology. Take a look at this picture of an integrated circuit. These are inside your computer, they're in your mobile phone, they're in calculators. These integrated circuits based on silicon, they have on them now billions of individual transistors. So each of these transistors is now defined on the scale of the nanometer. Tens of nanometers describe the spaces between the various electrodes that make these transistors operate properly. It's only because we have these tools, it's only because we have this capability to understand the materials making up a transistor in cross-section. It's only because we can engineer those materials on the right length scales. It's only because we understand the atoms that make up those materials and how the atoms making up those materials give rise to the electrical properties, insulators, semiconductors, metals. It's only because of that understanding and that scientific context that we have been able to engineer the computing revolution. In fact, it's because of our dexterity at that length scale that we can do more than simply compute. But we can sense our world. And so if you think of your smartphone and the fact that it's got an image sensor in it, it's got a GPS, it's got temperature sensors, it's got proximity sensors. All these are connected to multiple integrated circuits. The integrated circuits are talking to the rest of the world. They're talking to the internet through extremely high frequency communications channels, through wireless communications. All of these capabilities are directly traceable to our ability to engineer matter towards a specific purpose. And now what we've succeeded in doing, and the smartphone is a great example of it, is we've taken such a vast array of semiconductor technologies, such a vast array of building block materials, and combined them rationally in order to make devices that implement so many and integrate so many functions. In fact, the batteries that are inside your cell phone, increasingly they have achieved dense storage, so dense in terms of a lot of energy per mass and also dense in terms of a lot of energy per volume to make things fit into a very compact form factor. All of these are coming through our increased ability to engineer materials at this very, very short length scale. In fact, the fact that there's something for your cell phone to communicate with, the fact that there is an internet, is also enabled by some really important advances also on this length scale, coming, though, in this case from light, coming from the field of fiber optics. Today, we're able to send trillions of bits per second of information over a single glass optical fiber cable. A crucial piece of that was our discovery of how to make glass so pure and so perfect, so lacking in defects, that we're able to ensure that light is launched into one of these fiber optic cables and that it can bounce down and that it can travel over thousands of kilometers without the loss of power and thus without the loss of information. And the sources of this light, they have to be incredibly pure. They have to provide a single frequency that's extremely powerful, that's very focused, that we can couple into one of these optical fibers. And so it's the laser, in particular the semiconductor laser, that gives us this capability. With these lasers, we're able to make very, very pure, even coherent beams of photons, coherent beams of light that we can launch down an optical fiber and with which we're able to propagate information over these vast distances. You know, some of this may sound exotic, some of it may sound difficult to do, difficult to engineer. And in the first instances, before we knew how to do it, it certainly was. But what's so striking is that with many of these innovations, such as integrated circuits or fiber optic communications, what it's actually done is it's reduced cost. It's meant that the price of a long-distance call has fallen by an order of magnitude over the last decade or two. It's meant that we're getting increasing and increasing computational complexity and sophistication, but in fact at lower and lower cost per unit of computing. The advances that have described this field of integrated circuit engineering, computers, mobility, lasers, the internet communications, you can think of them as one branch of nanotechnology that I'll call top-down. And by that I mean we set ourselves upon a design of a device, a design of a material, and we then make an imprint. We convey that imprint using a technique called lithography, which is analogous to screen printing, the way we make t-shirts. We use this to, on a massive scale and on a very, very small length scale, to generate these billions of identical transistors and connect them together. But in fact, one of the most exciting things that's going on today in the field of nanotechnology comes at it from exactly the other side. It's what we call bottom-up nanotechnology, and it comes at engineering materials from the point of view of saying, through chemistry, we understand atoms, we understand their proclivities, we understand the propensity of one atom style to like to bind to another style of atom, from one element to interact with another element. And through that understanding, we're able to engineer materials that self-assemble. And so now, in contrast with the top-down, where we do have to define matter, carve up matter on the nanometer length scale, here we start from constituents, atoms smaller than the nanometer, and we introduce them to each other. We introduce them to interact with one another such that from the bottom up, they form new materials. One very exciting class of new materials that is very much at the heart of nanotechnology today is quantum dots, such as those shown here. And these are semiconductor particles a few nanometers in size that evince some very special properties. They're called quantum dots because they evince what we call quantum size effects. And through the quantum size effect, the size of the particle changes its resonance. What happens is that electron waves, because when we get down to the scale of the nanometer, we have to think in the rules of physics, the quantum world of physics, not just the classical. These electron waves get condensed or compressed down. And just like when you change the size or the tension on a timpani drum and you change its frequency, well, we change the frequencies, the resonances, and therefore the colors that these quantum materials emit. In fact, a similar idea of resonance is at play in the field of plasmonics. This is the area, such as with metal nanoparticles, that make stained glass have different colors. These different size effects lead to resonances in that case with light, to resonant interactions between the wavelength of light and the characteristic length scales at play within these plasmonic structures. There's another really interesting and important way in which getting down to the nanometer length scale ends up being really important in influencing the properties of matter. When we shrink materials down to these incredibly small length scales, we have the capability of fitting a huge amount of surface area into a finite volume. That ends up being powerful whenever we need a lot of surface. We often drive chemical reactions at surfaces. That is the field of catalysis. And in fact, catalysis is something that's already widely utilized and something very familiar in your own automobile. The catalytic converter is something that leverages having huge surface areas in order to convert noxious emissions into more environmentally acceptable ones. It's taking advantage of this huge surface area. Well, going down to engineering materials on the nanometer length scale gives us even greater access to the capability to refine and control materials and chemical reactions on these scales. Let me suggest one other interesting example of the power of nanomaterials and nanotechnology and of nanoscience, our ability to understand these structures. It comes from our ability to engineer new composite materials that have a number of properties all in combination. They can be incredibly light in weight, they can be very, very firm, they can be very strong, or we can engineer them to be flexible. You know, ultimately what the field of nanotechnology comes down to, for me, is making the connection between the form and the function of a material. As a scientist, it's to understand the connection between nanoscale, form, and then behavior. And as an engineer, obviously we're incredibly driven to try to take advantage of those insights, take advantage of that understanding, and then build designer materials tailored towards specific applications.
Now that you've been introduced to the nano world and a few of the technologies that nanoscience enables in computing and communications, we'll switch gears and we'll talk for a few minutes about how thinking about biology at the nanoscale can lead to similar advances in medicine. I'm Shana Kelly and I'm a professor of biochemistry and pharmaceutical sciences at the University of Toronto. My background is in the chemical sciences, and I run an interdisciplinary research group at U of T that works on a variety of nanotechnology projects. In this course, I'll be the one to take you through the aspects of nanotechnology that relate to biology and medicine. This is a very exciting field that is moving at a really fast pace and producing incredible advances in medical care. Now, Ted Sargent just gave you a great overview of the unique aspects of science and technology that come from taking the size scale of materials to the nanometer regime. For biology and medicine, going to the nanoscale also has a set of unique advantages. If we think about the biology that underlies physiology and the anatomy of humans, we realize that we have to focus in on the nanoscale to truly understand it. Cells are the most basic unit in living organisms. Ted already touched on the fact that the sizes of these units approach the nanoscale. Our bodies are made up of trillions of human cells, each of which is about 10,000 nanometers across. But cells can be smaller. Bacteria, for example, and we have lots of friendly bacteria in our bodies, are much smaller, about 1,000 nanometers. And some types, mycoplasma, for example, can be only 300 nanometers. So cells, our basic building block, are almost nanoscale. If we look inside of a human cell, we find that there are many structures and compartments, like the mitochondria that produce our energy. And these compartments are hundreds of nanometers. But what are truly nanoscale are the molecules that do all of the work in our cells. The pumps that move molecules in and out of our cells are tens of nanometers. The proteins that do all the work to keep our cells going are typically 5 nanometers in diameter, and the DNA molecules that program our genetics measure about 2 nanometers across. So the fundamental building blocks of life are molecules, and those molecules are nanoscale. The study of biology and biochemistry has changed so much over the last 50 to 60 years, and it's focused on the nanoscale more and more. Over the last several decades, we have developed really powerful tools to study life all the way down to its fundamental building blocks. The structure of proteins became known beginning in the 1940s, and then the structure of DNA was identified in the 1950s. Enzymes that allow us to recombine DNA in new ways were developed in the 1970s. And then the human genome was sequenced in the 1990s. So with every decade that passes, we have new ways to get more and more information about biology. So as you see, biology really operates at the nanoscale. And this means that nanotechnology is particularly relevant to medicine because in order to cure or diagnose disease, we need to know what's going on at this level. The drugs that we use to treat disease are all targeted at proteins or DNA molecules. And so to understand how drugs work, and in order to make better drugs, we need to understand what's happening at the nano level. Understanding the nanoscience of biology has already been proven to allow us to deliver drugs more effectively. Using nanomaterials that can be programmed to be much more specific than the macroscale materials we have used for drug delivery in the past, we can deliver a drug to where it's needed within the body rather than just letting it distribute randomly. Here's an example of a structure used for drug delivery. What you're looking at is an image of a carbon nanohorn. This is a carbon-based structure that is just a few nanometers across. Nanohorns are relatively easy to make. If you produce soot from burning organic matter, there will usually be some carbon nanohorns in the mixture that results. And the shape of carbon nanohorns really seems compatible with using them as containers. This nanohorn can actually serve as a nano-sized drug capsule. It can be filled with an anti-cancer drug, injected, and then it only releases the drug once it has reached a tumor. This type of nanopackaged drug has shown to be 100 times more effective than one formulated using existing methods, which instead use different types of solvents or chemicals to disperse a drug in solution. Now, of course, the ability to work on the nanoscale or the molecular scale means that we can see molecules more readily, and that's a huge advantage. If we want to diagnose disease earlier, when it's more treatable, we need to be able to detect the first few molecules that signal the presence of disease rather than waiting for symptoms to develop, which typically means that there are many molecules present. So to look for something as small as a molecule and do it with the sensitivity needed for early diagnosis, we obviously need really small detectors. There are a variety of nanomaterials that we now have in hand that are really good at giving off signals and providing high sensitivity to diagnostic tests. For example, gold nanoparticles are a very promising material for disease diagnosis and treatment, both because of their small size and because of their electronic properties, which are directly tied to being nanoscale. Regular gold, as you know, reflects yellow light. But nanoscale gold particles actually appear purple in solution. They absorb much longer wavelengths of light. In a few lectures, we'll spend quite a bit of time talking about this feature, which arises because of a change in the electronics of gold that happens at the nanoscale. What we'll learn is that this electronic feature can be harnessed to read out very small changes in the sequence of a DNA molecule, a capability that allows the diagnosis of genetic disease. Gold nanoparticles have many other important applications in nanomedicine. Recently, we've been able to engineer them to seek and destroy cancer cells. How does this work? Well, gold nanoparticles can absorb light and convert that light into cell-killing heat. And they can be made in a form that absorbs infrared light. And this is quite important. Unlike visible light that is absorbed by skin and tissue, we can actually get infrared light into a tissue. So we're able to get the signal into the gold nanoparticles even if they are under layers of tissue and skin. And this is very important for targeting tumors that are almost always under these types of structures. And these gold nanoparticles are really versatile. They can also be used to combat infectious disease. You're looking at gold nanoparticles that have found a dangerous type of bacteria. The nanoparticles that can be made to act as very sensitive and specific detectors of bacteria and other cell types for disease diagnosis have an added benefit. They can be activated and made to selectively destroy cells that are harmful. This is something that's difficult or even impossible to achieve with materials that are not nanoscale. And you can see that because of the small size of the nanoparticles. A group of them can actually gang up on a bacterium and attack it. This allows nanotherapies to deliver a stronger punch. Nanomaterials can also be used to generate new types of surgical tools. You're looking at two carbon nanotubes that have been attached to a stem to form a set of nanotweezers. Amazingly enough, we can bring the nanotube tips together so that they're touching and they're able to grip particles that are close to the size of cells. So if we want to perform more precise surgeries that are less damaging to healthy tissues, we'll need this type of nanotool that can take out one cell at a time. Another very exciting area of nanomedicine research is the work being done on the growth of artificial tissues and organs. Scientists can engineer hard and soft materials at the nanoscale using techniques like lithography or self-assembly, and these materials can be used to teach cells to grow in set patterns, the way they do in natural tissues. We've also figured out how to interface these nano-trained artificial tissues with a blood supply, which is great given that tissues need to be in contact with the blood supply in order to get oxygen and important nutrients. Working at the nanoscale to manipulate cells and build up tissues is how we finally made the breakthroughs required to get this to happen. Otherwise, we just couldn't get fine enough control to grow artificial tissues that are functional. Now, in all the systems I just told you about, we can visualize the nano-size scale of biology and the nanomaterials that we can use to manipulate biology with the imaging tools that Ted mentioned. Using these powerful types of microscopy is really one of the most satisfying aspects of working with nanomaterials. Despite the fact that nanomaterials and the basic building blocks of life are really small, things like electron microscopy are easily able to provide pictures. So we don't have to use our imagination really or do any guesswork. There are always pictures to look at. When I was a graduate student, I studied lots of different types of spectroscopy, and I made molecules and characterized them using spectroscopy. And there you never really get a picture of your molecule, but rather you get a pattern of signals that need to be interpreted. My dad, who's a civil engineer, would always ask me how I knew what kind of molecules I was making, and how could I trust a pattern of lines on a sheet of paper? Well, I always told him that I just trusted my spectroscopic tools 100%, but now to be honest, I'm much happier with the pictures that I'm able to look at that tell me exactly what a nanomaterial looks like. Throughout this course, you'll be able to look at lots of different nanomaterials and nanosystems. I'll rejoin you for a collection of lectures that will land really right in the middle of the course, where we'll look at biology and the range of ways that nanotechnology is enabling cutting-edge advances in medicine. I think you'll find this material and the promise of nanomedicine to be really exciting. But for now, I'll turn things back over to Ted, who will give you some thoughts on common themes uniting nanomedicine and nanotechnology, and then he'll lead you through the first main section of the course.
It might seem like Shana and I have been talking about pretty disparate things, biology, information technology, energy, and yet you'll notice that quite a few themes converge. They span what we're discussing. Let's think of a couple of examples. Well, I talked about huge surface areas being so important in the field of catalysis, really important area underpinning energy. When you think of the biological entities that Shana's been telling us about, they often have structures like the mitochondria in cells that are folded over one another, the way our intestines are folded up. They maximize surface area too. And in the case of mitochondria, they do it for the purpose of maximizing opportunities for chemical reactions. Another theme that cuts across these different fields of application is the theme of commensurability. The fact that in these quantum dots I was matching up the sizes of electrons with the size of the box that I was going to put them in, and that had a powerful influence on their properties. The fact that in the field of plasmonics, we see a commensurability, a similarity in length scales between the light waves that we will manipulate on the scale of hundreds of nanometers and the size of the metal particles that we can contain them in. And that there are applications of these that go well beyond information technology. Of course, in information technology, our currency is electrons. But in biology, often we use photons as reporters of phenomena that are occurring within cellular systems. And so these themes of commensurability, what they really come down to is our capacity to engineer matter, our capacity to utilize control and dexterity at the nanometer length scale in order to build materials having designer properties that don't occur naturally. Well, why is it then? What's the fundamental underpinning that leads to this commonality of themes that cuts across these different fields of application? Well, ultimately, it's that whatever Shana and I talk about, we're talking about using a common alphabet. Our building blocks within nanotechnology are the atoms, the elements that make up the periodic table. And further, we're utilizing a common grammar. The way in which these atoms assemble and form structures, the way they interact with each other, which ones can be juxtaposed and which ones will always remain apart. That is our grammar. That is the physics. That is the chemistry of the nanometer length scale. And so in the next lecture, what we'll do is we'll spend a bit more time on that alphabet and on that grammar. We'll understand what are the common scientific principles that underpin really all advances in the field of nanotechnology. That will put us all in a position together to think about a vast swath of exciting and important applications. It will allow us all to dream together in this incredibly creative space to use this palette of materials, palette of rules towards our objectives. And then throughout the rest of this course, what we'll do is we'll explore these implications and these applications together. I'll get to talk about the world of nanotechnology and information and communications technologies, how it's revolutionizing our ability to communicate information, compute, sense the world around us. Shana will take us through a fascinating voyage of discovery in the worlds of medicine and biology, and how nanomaterials and nanostructures and their commensurabilities, their surface areas, are allowing us new abilities to interact with organisms and really provide some solutions to our most important health problems. And then I'll get to talk about another really important societal problem and how we have some solutions to it through nanotechnology. This is the field of energy. We're all so concerned about our climate. We're concerned about what we're doing to our environment. Nanotechnology is giving us some opportunities to harvest the sun's abundant energy, to store the energy that we capture, and to replay it efficiently. I'm looking forward to this journey together.